Good afternoon and welcome to today's STS-107 mission status briefing. With us today is Phil Engeloff, the STS-107 mission operations representative, Dr. John Charles to his right, the STS-107 mission scientist. To his right, Dr. Arnie Ferrando, of the principal investigator for the protein turnover experiment, and Dr. Scott Smith, who is the principal investigator for the calcium kinetics experiment. We'll start with brief notes from Phil and John and then go on to our other briefers. Phil?
Thank you, Kelly. Okay, well, we had a real good weekend. For those that have been following along and were aware of the thermal issues that we wrestled with last week, we have overcome most of that problem. We're over the hump, and with some of the larger heat-generating experiments having completed their operations, the cabin temperatures have fallen back into a pretty comfortable level. Both the crew module temperatures in the orbiter and the temperatures back in the space hab are running around the mid-70s. It varies with the amount of activity going on at any given time, but it's down at a very comfortable level, and we don't foresee any more problems through the rest of the mission. So we think we're in a good, stable configuration and don't anticipate any more problems with the cabin temperature. With that, the crew is in great spirits. They're working through the timeline and doing a great job keeping up with everything. I think we've done just an absolutely superb job executing all of the tasks on the list for the crew. And I think the science community is very happy with the progress that we've made to date, and we're looking forward to a good, successful completion of the mission this weekend. Some of you may have seen we had a little sort of lighthearted ship-to-ship communication between the orbiter and the space station just a couple of hours ago. For those of us on the ground, that may not seem all that novel. We can pretty much call the crews on either vehicle and talk to them at any time, but we like to take advantage of these opportunities. It does add a little bit of interest and lighten the day a little bit for both crews to get a chance to talk to each other from space, and that was a little bit of fun for everybody. As I say, the mission is going great. Everybody's happy, and we're looking for a good continuation of the week here through the end of the mission. John?
Thank you, Phil. And like Phil says, the crew is enthusiastic and working very well for us, accomplishing our science activities. We're going to hear about two of those science activities, some of the medical experiments we have going on board from Dr. Ferrando and Dr. Smith in a second. Let me catch you up first on the activities over the weekend. In the area of fundamental biology, we are close to wrapping up the brick experiment, the biological research in canisters growing moss in the absence of gravity, and after a little while in the absence of light that helps it grow in the direction it's accustomed to. Two parts of that experiment have wrapped up or are wrapping up very soon, and a third part of that experiment will wrap up in the next several days with a series of fixations of the moss plants so they can be analyzed in their different growth stages after flight. The biopack experiment of Barry Pyle has finished up some final bacteria samples being successfully fixed and placed in cold stowage after their 48 hours of growth. In the area of human life, and also BioTube, another experiment is starting up on flight day 13 toward the end of the mission. In the area of the human life sciences, the Blue Flight Day 12 crew took their oral tracers and did their blood collections and IV tracer infusion as planned earlier today. The Red Shift, which is on duty right now, is in the midst of doing all that stuff, and oral tracer ingestion, blood sampling, and be administering some intravenous tracers and more blood collection this afternoon. As I said, our speakers will tell us a little bit more about that in a second. Right now, everybody's the payload crew members are also collecting their urines and as well as bloods over the next several days. The sleep study is continuing as nominal. It's essentially wearing a piece of hardware that monitors the crew members' activity and the light levels, and they're doing some questionnaires and logging before and after they wake up. And the microbial physiology flight experiment, which had some difficulties last week, has completed or is soon to complete its activities. The last card tray incubation is being completed, and following that, the AMS hardware will be deactivated. I reported last week that the AMS was moved to the middeck in search of a cooler location. In fact, that was not correct. Certain components of the experiment were moved, but the AMS stayed in the module. In the area of microgravity sciences, the mechanics of granular materials is going to wrap up with its 10th and last run scheduled for later today using a reformed load cell. You saw last week a discussion of the load cells that are used for those compression studies. This load cell was that it's a very high priority to accomplish during the course of this mission. The principal investigators are very happy with the results of the investigation, as are all the other principal investigators. And with this load cell study being finished today, they will call themselves very successful. We finished up softball, the flame balls experiment over the weekend, just wrapped it up, pulling the hardware out of the combustion module last night or this morning. The softball accomplished overall 39 tests with 15 different fuel-air mixtures, producing a total of 55 flame balls, many of which got named by the crew and by the ground support folks, with a total burn time of over 6 hours, 6¼ hours. And amongst the accomplishments of the flame ball study was the weakest flame and the leanest flame mixture ever produced anywhere, I say in the universe. That may be a little bit presumptuous. The longest lived flame of 81 minutes lasted almost a complete trip around the Earth. And there were several new results that the investigators are very happy about, including some oscillatory expanding and contracting behavior of the flame balls that is very interesting to them in terms of what it tells them about the dynamics of combustion processes. So that'll be replaced now by the water mist experiment in the combustion module. There are some activities going on today with the equipment being installed into the combustion module. Some early testing reveals some difficulties getting that going, so that has been pulled out, the connections checked, and that's being put back in. KC Chawla worked on that this morning and handed over to Ilan Ramon so she could continue with the last MGM, the Mechanics of Granular Materials run. So Ilan is working on that right now. We anticipate that being completed and the test run finished up, and hopefully saving enough time as we go along to make sure we get as many of the water mist runs done as possible. The bioreactor, the biotechnology demonstration system, continued over the weekend with media sampling and regular video downlinks. We'll hear about that tomorrow from Tom Goodwin. And the other activities in the NASA payload, astroculture, that is the roses growing in space, and other experiments are continuing as before, mostly right now wrapping up and continuing to monitor and collect data. So that summarizes pretty much the activities over the weekend. I'm going to ask Dr. Ferrando now to talk a little bit about his research in protein turnover on this mission.
Thank you, Dr. Charles. As Dr. Charles mentioned, one of the experiments they'll be performing here very shortly is called protein turnover during spaceflight. And what it is an attempt to look at some of the reasons why the astronauts lose body protein when they're in space. It is an experiment that, much like Dr. Smith's here, it uses some fairly sophisticated methodology and tracer methodology whereby we study these astronauts twice before they go in flight, twice during flight, once early in flight and once later on in flight, in an attempt to see if there's any adaptive mechanism as space flight continues. And then again after they return, once early in return and once later, to once again get an idea of the adaptive mechanisms of the body. So what we're looking at here is how the whole body makes and breaks down protein, and in particular how the muscle makes and breaks down protein. And this is a very unique experiment for us. Most of my work normally deals with trauma and aging research here or at UTMB. But the interesting thing about this, from a design or scientific standpoint, is it gives you an opportunity to examine a stress state, if you will, on a healthy individual, because all the stress states that I deal with have some accompanying injury, disease, or pathology with it. But yet here in spaceflight you have and I say it's a stress state because the human organism is not used to this. So it's a stress state that I get an opportunity to study and look at its effect on these body systems, and in turn muscle protein in particular. And hopefully we can, from what I can tell so far based on our work on STS-95, it looks like for some reason the body just decides it doesn't need to make protein anymore, and that whole process dramatically slows down such that the body just loses more, breaks down more than it makes, and as a result over time muscle protein is lost. So once we understand entirely all the mechanisms responsible for this, the idea of course is to propose some countermeasure, mostly like what we use here on Earth in our patient population, that will help ameliorate this loss and keep them functional for longer terms. One of my collaborators on this project, and who's helped me out a great deal, speaking of all the NASE's part of this is Dr. Smith, so I'll let him tell you a little bit more about all the props and tools that we use to ascertain this.
Thanks, Arnie. Good afternoon. I'm the principal investigator for what we call the calcium kinetics experiment. And what that means is that we're trying to understand the movement of calcium in the body. And the way we do that is by using special, what we call tracer techniques, where we give a special form of calcium to the astronauts. One of them is taken orally, and another one is injected intravenously. And we can then follow these forms of calcium through the body. And that's what the astronauts are doing right now. We've had a great session on orbit. The crews have done just an outstanding job. On Flight Day 3 was one of our biggest flight days, where the crews took, again, both the oral and intravenous tracers. This morning they took another calcium tracer that will allow us to follow the calcium through their bodies during spaceflight. Now, one of the nice things about these tracer studies, even though they're a little more complex to understand, is that it does allow us to study these things during spaceflight. There are different ways to study bones. You can do whole body X-rays, which of course we can't fly in space. You can take bone biopsies or take a little chunk of bone out. But most of the astronauts we've asked haven't been real keen on that. So we've reverted to these other techniques that allow us to essentially collect biological fluids, things like blood, urine, saliva, that allow us to measure what's happening to calcium metabolism during spaceflight and how that changes. We studied the astronauts before they went up. We studied them at the beginning of the flight, now toward the end of the flight, and we'll study them again after they get back to try to get a handle on why astronauts lose bone during spaceflight. As you know, bone loss is one of the most critical challenges that we face for long-duration spaceflight, and getting a handle on what those changes are, how they occur, and most importantly, how we can counteract them is very important for the space program. Two things that tie into that. One is that we always not only need to look out towards further exploration missions, but we also look at what is the research we're doing and how can that help people back here on Earth. Obviously, there are a number of bone diseases on Earth that are very similar to what we see during spaceflight. The one that comes to mind most frequently is osteoporosis. And also, if we look at individuals that are paralyzed, are both very severe cases of bone loss. And our hopes are obviously that if we can help to stop the bone loss during spaceflight, that we can also spin some of that research and spin some of that technology back to the general population to help them as well. The other thing we've done in NASA, one of NASA's primary goals is educational outreach. And we've done an extensive amount of work with the calcium kinetics experiment to work with schools across the nation and literally around the globe to help do a few things. One is to let kids know that what it takes to do science during spaceflight, that there's an entire experiment team, that there's a lot more to space research than the astronauts on board the shuttle, that the process is the same that you would for a science fair project, if you will. It just takes a little bit longer, and the scale is usually a little larger, but you need to come up with a hypothesis and ask your questions and get your materials and go and collect your data. And right now we're obviously very excited to be in the data collection phase. To share some of this with the schools, I just got off the phone with a fourth grade class in Freeport, Texas, to talk to them, to tell them about what we're doing and where we are, and to sort of chart this process over time. We developed what we call the Adopt a Classroom program, where we started with one, and we're up to, I believe, 6 or 7 different schools that we've sent newsletters to once a month that allow the kids once a month to look at where we are and what's going on. We started this back in early 2001. And sent these out once a month to the school, again, to try to give a feel for the different aspects of what's going on. You can see there on screen what an example of what the newsletter looks like. It's just a one-page, two-side paper. And we included different aspects of it. Again, we talked about the mission and where we were. We talked about different people on the team to highlight different aspects of the workers. That is, we had one month we talked about the astronauts, one month we talked about scientists, we talked about dietitians, we talked about engineers, we talked about chemists, to help give the kids a feel for the fact that NASA generates a lot more in terms of jobs all the way across the board, that astronaut is not the only position down here. And then not only in terms of exciting the kids about science at NASA, we also cheated some, which is to provide some nutrition information. That is, if we can tell the kids why calcium is important and why bone health is important, it's actually most important in their age groups. Most of your bone mass is laid down by the time you're 20 years of age. So if you're looking at curing osteoporosis, getting information into kids when they're 5 or 10 or 15 years old, actually gets you a lot further down the road than trying to help somebody when they're 65 or 70. So we really have worked across the board to try to help hit each of NASA's goals. Again, the basic science to help us explore the outer edges of the universe, helping the planet Earth from all ages, and it's an incredible experience to be here on flight day 12 after working some 4 years to get to this point. I know I sound a little tired, or at least I feel a little tired, but it's incredible to be here. And with that, I'll turn it back to Dr. Charles.
All right, thanks very much, Dr. Smith. Tomorrow we're going to hear from Tom Goodwin, principal investigator for the bioreactor cell growth experiment, and I think that'll be it for now. Kelly?
Okay. We'll move now into question and answer phase. If we have any questions here at JSC. Juan?
Juan Lozano with the Associated Press. I guess this is for Phil Engeloff. I guess if we could just go a little more detail as far as with the heater problems on the orbiter, I guess as far as what specifically was done to fix that, where you're not having any problems with that now.
Okay, just to kind of go back and give a thumbnail recap of the events last week. In the orbiter and in the space hab, we chill the air by blowing it over a radiator, essentially, that's got cold water flowing through it. And the natural result of that can be condensation. And we take that condensation off with some little rotary devices, sort of like fans that centrifugally sling the water out to the outside and push it off into a tank. We have 2 of those in the orbiter, in the middeck, and 2 of those back in the space hab. The orbiter chills water and sends it back to the space hab to cool that radiator or heat exchanger. And we had problems with both of the rotary separators in the space hab. And as a result, we had to turn those off. The problem we had there is if you were to continue to blow the air over that heat exchanger, you'd get condensation, but you wouldn't move that away and you'd just collect water under the floor. To avoid that, we warmed up the temperature of the water going back to space hab so that it was above the dew point of the air back there. And in order to compensate for that loss of cooling, because we were now not cooling the air in the space hab with that chilled water, we essentially turned the temperature down in the orbiter and chilled the air in the orbiter to a colder temperature and blew that back into the space hab. We always have a certain amount of air exchange back there because we take all of the carbon dioxide out of the air in the orbiter and provide for those kinds of functions. But by providing this additional cooling, we cooled the air temperature down in the space hab. Now, that wasn't quite as much as we would have liked to have, so the temperatures in the hab last week went from the usual 72, 73, 74 degree range up into the 82, 83. I think we peaked about 84 degrees at one point. And that was tolerable for the crew, but not very comfortable. We then had to do a little bit of additional work as we ran some of the experiments that generated a lot of heat. The cooling loops, the water loops, not only are used to cool the air, but we also run those directly through some of the experiment racks, run that water through the experiment racks to cool the experiments locally. And we played with some diverter valves that the Space Hab folks gave us some direction on and allowed the crew to adjust the ratio of cold water going to the heat exchanger versus going to the payload racks. And again, we got to a point where we could get by and provide enough cooling for the experiments without compromising the cabin temperature level to a degree that the crew couldn't work back there. Since that time, we've finished some of the high heat load experiments, like VCD specifically. That was one of our concerns. We could always run any of the experiments. We couldn't just run them all at the same time. We've gotten over that peak of high heat load, and we're now sort of in the area where this compromised airflow and water cooling loop configuration is adequate for all of the experiments are running, and it's keeping the cabin air temperature down in a pretty comfortable 74 degree range.
And I guess this question for Dr. Charles. I guess on the problems with the water mist experiment today, I know you talked about it a little bit earlier, but as far as, I guess we just, a little bit more details as far as what specifically was happened with that, and I assume that it'll be fixed by, it'll get going today then.
We're hoping it'll be going by the time we finish this briefing. What happened was that certain certain fittings, connections had to be made. As you pull out one set of experiments and put another set of experiments into the combustion module, certain airtight fittings have to be made so you can pump the fuel mixture, or in this case the air, into the combustion chamber. You can decompress around the test item as appropriate. And as they went through their pre-test, they found indication that the airtight fitting wasn't airtight enough and it was leaking, and so the malfunction procedure is simply to disconnect everything and try again. This being the flight hardware, the fittings are very stiff. They're not broken in like the trainer units are. It's easier. It's usually easier in almost every training item to make the connections than it is in the flight hardware. So we're betting that the crew thought they made good tight fittings because they felt tight, but they probably can be just a little bit tighter. So the disassembling and putting it back in, and hopefully by the time we get back after this briefing, we'll find out that those connections are now indeed airtight and the experiment's ready to go.
All right, that's all the questions here in Houston. We'll go now to Kennedy Space Center in Florida.
Hi, this is Phil Chen, Earth News for Phil Engelhoff. I was kind of surprised at a couple things on this mission which didn't make me think that I was following the right flight. Why are you using LIHO canisters rather than the RCRS system that's been used in the previous EDO flights? And what are you using the contingency water containers for? I have no doubt you're not filling them to bring over water to space station.
That's correct. As far as the CO2 removal, there's always a trade-off in stowage. The RCRS, the regenerative CO2 removal system, basically takes up a big volume underneath the floor that we usually use to store the lithium hydroxide canisters that you refer to. But in addition, we still have to carry some of those canisters for contingency cases should the RCRS fail. In this particular case, because of the amount of cabin stowage that was involved with this vehicle, it was actually more space efficient to use the lithium hydroxide canisters. And as far as the extra effort to sort of bring the RCRS back out of retirement, so to speak, outfit it into the vehicle, and then change the vehicle back to the other configuration before its next mission to space station, it was just more efficient to go with the lithium hydroxide canisters. On your second question about the CWCs, as I mentioned, we had originally had a configuration here where we would be collecting condensate in the space hab, but we don't have an infinitely large condensate tank back there. And so as we filled that tank, the intent was to then fill CWCs full of water, bring them back forward into the orbiter, and dump them through the orbiter waste system.
Okay, so I assume that with your changing around of the temperature valves and doing all the water removal on the shuttle side, you have less water bags to carry back and forth.
Basically, we only have the water that we accumulated in the early part of the mission.
And early on, you had said in one of the briefings that you were fairly fat in terms of cryo margins. How do you stand now, and as far as other margins? And we had been briefed before the mission, there's no plans for mission extension. Is that still the case? And just save that in case you need extra weather wave-off days.
All of that is correct as you stated it. We carry right now about 2 days and 8 hours of on-orbit margin at average mission usage levels. For mission extension days, with the powered down state, we can stretch that out to something more like 2 days, 20 hours or so of extension capability. In addition to the cryo that we would use for power, we have adjusted the lithium hydroxide usage based on the actual CO2 production, and we've essentially staged that LIO to the point now where we can support a total of end of mission plus 4. In other words, the usual end of mission plus 2 days extension, plus an additional 2 days of extension. And we have plenty of propellant to use should we fall into that mode of dwelling on orbit, waiting for good weather. But as you also pointed out, the program stance right now is that we will not be extending other than for weather violations for nominal landing.
Hi, it's Chris Kreidler from Florida Today with a question for John Charles. Do you know offhand what some of the names, what names were used for the flame balls?
Come to mind immediately. One was Karen, for Karen Weiland, one of the project scientists for the combustion module experiment for softball, and the other one was Kelly, named for who I don't know, but I think most of us were not unhappy or not offended, at least, that we didn't get flame balls named after us. But there was a large number of names. And they seem to be sometimes the crew members and sometimes people on the ground that the crew trained with, sometimes family members. I don't know anything else.
This is Phil Chen again. I guess for Phil Engelhoff, are there any plans for anything special tomorrow at 11:38 Eastern, 10:38 your time, either in mission control or in orbit?
I can say truthfully that I'm not aware of any plans that the crew may have on orbit. There are some local observances scheduled here as opportunities. There's not going to be a formal ceremony of any kind, but there are a few informal activities springing up around the center. And for those of you that may be wondering what Phil's referring to, tomorrow will be the anniversary of the Challenger, and we've gotten into the habit of recognizing essentially all of the people who have lost their lives in the service of this program, both in the Apollo 1 fire, the Challenger accident, and any number of other incidents over the years.
And can I ask each of you to say where you were 17 years ago tomorrow, and were you watching it live, or how did you find out about it, and what was your reaction at that point?
I guess I'll start with that one. I was in a conference room here. I had just finished the mission just prior to 51L. I was a flight planner back then, and I was on a floor in the third floor of Building 4 with a bunch of my cohorts in a conference room watching the launch, and I'm not sure I can adequately describe publicly here the reaction that each of us had. These were our friends that lived down the hall from us in our offices here. They were heroes every day to us. This was our job, our life, and our career, and there was a lot of uncertainty for all of us as to what this was going to mean. But I think within a pretty short period of time, and I mean within hours, I think people had adjusted to a state of optimism that we were going to go find out what happened and pick up and carry on. And 17 years later here, it's kind of nice to see that we in fact did that and picked up with that legacy, and are here today with the space station occupied 365 days a year and an independent shuttle program serving both the station and the broader science community and the objectives that all of those people stood for. So I guess that's probably more than I needed to say, but John?
Yeah, and Phil, I had just come back from an off-site meeting. I'd parked my car and walked into Building 37 to go to the conference room to watch the launch. So I came in just in time to see everything unfold. And the rest is, as Phil said, the uncertainty, and then followed very quickly by the determination to do whatever we had to do to among the scientific community, get the program back going again.
Well, my path's actually quite different. I was an active duty officer in the Army at that time. I was a pilot, and I actually was an instructor pilot. And we actually watched that between flight shifts. We were about ready to go out and get in the aircraft and fly our missions, and we actually watched that. It was back then, of course, they were all still very novel, and everything came to halt. This was at Fort Rucker, Alabama, the Army's training site, and everything came to halt, and everybody stood down and watched it. It was quite a sobering event, as you can imagine.
I was in graduate school at the time, working in a basement laboratory without any exposure from the outside. So it actually took, I think, about 30 minutes to an hour before somebody had actually called down to let us know what had happened. And of course, the reaction is hard to describe. But obviously, to be here 17 years later is an incredible testament to the people that have come before us and continue to strive to take that next step.
So from the Static Test Road VIP site, and as you said, it's an experience we'll never forget, but appreciate your insights. For the calcium kinetics experiment, has there been, I realized...
But obviously to be here 17 years later is an incredible testament to the people that have come before us and continue to strive to take that next step.
So from the Static Test Road VIP site, and as you said, it's an experience we'll never forget, but appreciate your insights. For the calcium kinetics experiment, has there been, I realize that most astronauts are a little bit resistant about the concept of a bone biopsy in space, But on the other hand, I know a lot of scientists and others who would be glad to fly if that was the provision. Has there been any thought about actually doing anything like that? I know there have been muscle biopsies in quite a few astronauts, and they've been happy to do it because they've realized the importance for the science.
Well, you could do, I joke about the bone biopsies, and certainly you could do those. We're actually quite happy with the techniques that we have. The information we get is outstanding. We do some incredible mathematical modeling techniques with the assistance of our co-investigators that allow us to actually measure the amount of calcium going into bone and the amount of calcium coming out of bone and the rate of movement throughout the body. So I actually think we get a better picture of what's going on in terms of the regulation of calcium and bone metabolism than we actually would with a bone biopsy.
Okay. I understand that's all of our questions from Kennedy Space Center. A few scheduled programming notes for you. Coming up at 2:39 p.m., we're expecting the Blue Team wake-up call. On board the Space Shuttle Columbia, our video file from NASA headquarters will be at 3 p.m. Central Time, and our International Space Station Expedition 6 commentary update will be coming up at 4 p.m. Today's Mission Flight Day Highlights package is scheduled to start airing at 7 p.m. A reminder that all this information presented here today and more is available on the NASA Human Spaceflight web at spaceflight.nasa.gov. Thanks for coming today.